A ship in the open ocean has no fixed markers. There is water in every direction and a curved horizon that offers no distance, no bearing, no confirmation of movement. The vessel travels forward, but its position relative to land cannot be observed. It must be determined indirectly. The sky provides the only reference. The sun moves across it in a predictable arc. Stars appear in fixed positions relative to one another. The moon follows a slower rhythm. These movements are constant enough to be measured, and measurement can be converted into position. But the process is not direct. The observer does not see latitude. He sees an angle between a star and the horizon. He records the time. He consults tables. He performs arithmetic. Only then does he obtain coordinates. The work is repetitive, technical, and vulnerable to error. It was performed on every long voyage for more than 2 centuries. It kept ships from becoming lost. It did not prevent all disasters, but it reduced uncertainty to a degree that made transoceanic travel possible.
The sextant was the primary instrument. It measured the angle between a celestial body and the visible horizon. The frame was brass or bronze, shaped in an arc of 60 degrees. A small telescope extended from one side. 2 mirrors reflected light along different paths, allowing the observer to align the image of the sun or a star with the horizon line. The angle was read from a scale engraved along the arc. The device was small enough to hold in both hands. It weighed between 2 and 4 pounds. Precision was essential. A deviation of 1 minute of arc could introduce an error of 1 nautical mile in the calculated position. The chronometer provided the second measurement. It was a mechanical clock designed to maintain accurate time despite motion, humidity, and temperature variation. It was mounted in gimbals and stored below deck in a padded case. The navigator carried the exact time in his mind or on a slip of paper when he went above to take the sight. Charts and tables completed the kit. The charts showed coastlines and known hazards. The tables listed the predicted positions of celestial bodies at every hour for every day of the year.
The navigator took sights at specific times of day. The most common was the noon sight, when the sun reached its highest point. This gave latitude directly with minimal calculation. Morning and evening sights used stars. The horizon had to be visible, and the stars had to be bright enough to see through the sextant's telescope. Twilight provided the best conditions. The observer stood on deck, braced against the roll of the ship. He aligned a reflected image of the star with the horizon and locked the measurement. He noted the exact time from the chronometer. He recorded both values in the logbook. The process was repeated with additional stars to confirm the result. Each observation lasted only a few seconds, but preparation and recording extended the routine to 15 or 20 minutes. Weather often interrupted. Clouds obscured the sky. Rough seas made it difficult to hold the instrument steady. On some voyages, days passed without a successful sight. The ship continued moving, and the uncertainty grew. The measurements were useless without calculation. The navigator retired to the chart room with the recorded angles and times. He opened the nautical almanac, which listed the celestial coordinates of the sun, moon, planets, and prominent stars for every hour of the year. He found the entry corresponding to the time of the observation. He compared the predicted position of the celestial body with the measured altitude. The difference between the two, combined with the azimuth, allowed him to plot a line of position on the chart. A single sight produced only 1 line. The ship was somewhere along it, but the exact point remained unknown. A second sight, taken from a different star or at a different time, produced a second line. The intersection of the 2 lines marked the ship's position. The arithmetic was not complex, but it required concentration. Tables of trigonometric functions simplified the work. Logarithms reduced multiplication and division to addition and subtraction. Mistakes were easy to make and difficult to detect. A transposed digit could place the ship hundreds of miles from its true location. Celestial navigation was not optional. Commercial shipping depended on it. Trade routes crossed oceans where no landmarks existed. Cargo vessels, passenger liners, and fishing fleets operated far from shore for weeks at a time. Military navies required it as well. Warships moved in formations across open water. Accurate positioning allowed them to rendezvous, to avoid collisions, and to find targets. Exploration relied on the same methods. Expeditions to polar regions, uncharted islands, and remote coastlines used celestial sights to map their progress. The institution of navigation was embedded in maritime culture. Officers trained for months in the use of the sextant and the interpretation of tables. Examinations tested their ability to perform calculations under pressure. Ships carried backup chronometers in case the primary instrument failed. Entire careers were spent refining the process. The system functioned because it had been practiced and corrected over generations. It was not perfect, but it was reliable enough to be trusted.
Electronic navigation systems appeared gradually, then replaced celestial methods almost completely. Radio direction finding became available in the early 20th century. Coastal stations transmitted signals that ships could use to determine bearings. LORAN, introduced during the Second World War, allowed vessels to calculate position from the time difference between synchronized radio pulses. The systems were faster and required less training. By the 1960s, ships carried receivers as standard equipment. Satellite navigation followed. The first systems were military, but civilian versions became widespread by the 1980s. Position could be determined continuously, in any weather, without consulting the sky. The sextant remained aboard some vessels as a backup, but it was rarely used. Training programs for celestial navigation were reduced or eliminated. The skills faded. Younger officers learned to navigate using electronic displays. The older methods were acknowledged as historical, not practical. The transition was not sudden, but it was thorough. Within a generation, celestial navigation had become a specialized skill rather than a fundamental one.
Training manuals were still published for several decades after electronic systems became standard. They explained the theory of celestial mechanics, the construction of the sextant, and the use of sight reduction tables. The manuals were used in maritime academies, where celestial navigation was taught as part of the curriculum. But the emphasis had shifted. Students learned the principles, but they did not practice the procedures with the intensity that earlier generations had. The examinations became formalities. Officers were certified in celestial navigation, but few of them ever took a sight aboard a working vessel. The manuals remained in libraries and storage rooms. They documented a process that was no longer central to the profession. Some vessels retained them as references in case electronic systems failed and the crew needed to revert to older methods. That scenario became increasingly unlikely. The equipment itself was more reliable than the people who had once operated it. The manuals collected dust. They were not discarded, but they were not consulted.
Sextants were stored in cases and lockers, intact but unused. They had been precision instruments, maintained carefully and calibrated regularly. Now they were kept as artifacts. Some remained aboard ships, tucked into compartments that were no longer accessed during normal operations. Others were donated to maritime museums or sold to collectors. The devices still functioned. The mirrors still reflected. The scales were still accurate. But there was no need to measure the sun's altitude. The chronometers followed a similar path. Mechanical timekeeping had been critical when a few seconds could translate into miles of error. Electronic clocks were more accurate and required no winding. The old chronometers were retired. Some were displayed in glass cases. Others were forgotten in storage. The transition was quiet. There were no ceremonies marking the end of celestial navigation. Ships simply stopped carrying navigators who knew how to use the instruments. The tools outlasted the practice, but not the need. Ships continued to cross oceans. The routes did not change. Cargo moved between ports on the same schedules. Passengers traveled the same distances. The vessels themselves became larger, faster, and more automated. Navigation was handled by systems that required minimal input. Satellites transmitted position data continuously. Computers processed the information and updated charts in real time. The bridge crew monitored displays rather than calculating angles. The work of determining position had been externalized. It was performed by machines that operated beyond the ship, beyond the horizon, beyond the atmosphere. The sky was still visible, but it was no longer consulted. Stars rose and set without being measured. The sun crossed the meridian without being noted. The ship moved forward, and its position was known at every moment. The voyage continued even after no one needed to look up. National Hurricane Center final report classified Sandy as Category 3 at maximum intensity and Category 1 at New Jersey landfall on October 29th at 7:30 p.m. local time near Brigantine. The World Meteorological Organization retired the name Sandy from future use in May 2013. NOAA's damage assessment determined it was the second costliest tropical cyclone in U.S. history after Hurricane Katrina. Federal Emergency Management Agency distributed $15.4 billion in disaster assistance. Post-storm engineering analyses documented surge return period of 500 years for Lower Manhattan based on statistical modeling. Infrastructure modification programs initiated in response included barrier systems, subway floodgates, and electrical substation elevation. The event became reference case for urban coastal vulnerability studies and climate adaptation planning frameworks.